Alright guys, it's 101 here, and today, redstone! Yay, lots of redstone. I am returning to building computers and crazy stuff with redstone again because of the 1.5 update. And you might be thinking, oh, he's going to do stuff with comparators and with hoppers and crazy stuff like that. No, I'm not even slightly interested in hoppers. Or maybe in a survival setting, but in redstone, no. I'm not even slightly interested in comparators either. Sure, we can make a 1-tick XOR now. Woo. My computer can be 1 tick faster than it was last time. Well, maybe 2 or 3, but still, I'm not interested in that in the slightest. What I am pleased with is that they finally fixed the bloody hash set problems. In the entire time I've been playing this snapshot, I have not seen a single derped out piston. For those of you who haven't seen one, they look like a piston, but it's both extended and retracted at the same time. I would show you one, but I can't because they're not here anymore, which is amazing. So that is allowing us to make huge combinational complicated systems and not have to worry about component design and all the nitty-gritty of it. We can sort of remove ourselves from the design of the individual components and just treat them as components that we can just assume will work in their positions, which is good. It means we don't need to do very, very deep debugging anymore. So, without further ado, let's get started. Now, some of you might recognize this thing as the first Minecraft CPU I ever built. It's very old, it's about a year old now, but it's so archaic and so damn simple and so slow, I cannot for the life of me imagine any situation in which it would break. In fact, I'm 99.9% sure it still works, but it's very laggy, and I'm not going to run it because it's not very interesting. There's a video on it. I'll put a link on screen if you want to see that, but yeah. So the first thing I'm going to do is I'm going to show you a few things I did in the update. A few things that didn't seem to work before the 1.5 snapshots, and now do work. So, I'll be back in just a second with the first thing to show you. Alright, so here's the first thing I want to show you. And this is a display, as you can probably tell. It's a very fancy display, actually. It does a lot of things that I've never really built a Minecraft display to do. But, anyway, let's go. Now, this is fancy because it does a whole bunch of stuff. For example, as you can see, there are no leading zeros. There is special logic for blanking leading zeros. There's also support for a negative sign, so you can have a negative sign. That negative sign will move depending on the length of your number, so you won't have a negative sign over there and then a small, like, 12 over here, because I've provisioned against that. It also has dividers every 3 digits, and that makes it very easy to read. You can't see the dividers now because they're switched off, because we've only got 1 digit. But, what does it do? Well, you input a 24 bits 2's complement number, and yeah, 24 bits is quite a lot, as some of you probably know. But, of course, you can shorten this. You can just move the sign bit over and punch out a few wires, and immediately you can use like an 8-bit or a 3-bit or a 7-bit or a 22-bit or a 23-bit or whatever. You can use whatever you want. Anyway, I'll label the individual parts, but I won't really tell you, I won't explain to you in detail how they work, because that deserves an entire video on its own. I spent a long time building this. So, first thing here is this block, and this is the input block. I'm going to enter a number. We're going to enter the number 511. So, that's a 1, a 2. It's basically just the first 9 bits on. It is 9. Yes, it is 9. I am capable of counting. And now we're going to tell it to go. Actually, I'm not going to do the first. No, we're going to do a bit more. That should be 1023. So this button here refreshes the display. Now it's quite slow. I mean, this little line here has to go all the way to the end to finish decoding the number. And the reason it takes so long is because the number is being decoded by this double dabble decoder. And what double dabble is it's an algorithm for converting binary into binary coded decimal, which is the decimal number we understand. Now 1023 would be something weird with letters in it in hex, but with this display it doesn't come out in hex, it comes out in perfectly understandable decimal. 1023. As you can see, we've got our little divider there. So there you go. Because this display is 8-bit, not 8-bit, 24-bit 2's complement, it'll display numbers between positive and negative 8,388,607. So it's got quite a big range. That's 7 digits. That's quite a lot. And of course we've got the negative sign over here, and the negative sign obviously moves. So there you go. Quick overview of the parts. We've got the 2's complement to sine and magnitude converter here. That makes takes the number that you put in, converts it from the 2's complement representation, the binary representation of that number, and changes it into just the number and the sign. So -3 is now -3 rather than it's a minus sign and a 3 rather than whatever the binary representation for -3 happens to be. So there you go, that goes into the double dabble decoder, which works on serial. This was not designed by me, that was designed by somebody on the RDF, either Redstone Warrior or Invalido1. It was designed a long time ago, but so I don't actually know who did it, but yeah, I didn't design that. Then it goes into a register. We've got the logic for moving the minus sign and blanking leading zeros here. So when I say blanking leading zeros, you can see that these first 4 displays don't have zeros on it. So you don't have a 00001023, you've just got 1023. Then we have these, and these just take the binary number, or the binary coded decimal block, and convert them into whatever signals are necessary to make the 7-segment display do what it should. So there you go, there is a nice fancy display. I will just quickly show it doing a negative number. I'll need to figure out the right input, we'll need to do the 2's complement stuff. I'll be back in just a second. Alright, so I've entered a new number. It's -1023. I wasn't very inventive there. So again, we can let it decode. You should also see that the numbers all change in sync. We don't have any sort of unsynced changes here. Whoop, there's your negative sign. It looks a bit offside, but it's not. It actually uses the display, the middle section of the display, to do its thing. So it looks a little offset just because there's a 1 there and not another number. So yeah, there's my fancy display. I'll be using something similar to this, probably a smaller one, on my new redstone computer, which I will build eventually. Alright, over to the next thing. Okay, so here's the second little thing I wanted to show you. Now, this didn't work at all in the other update. It didn't work at all in 1.4. I don't know why, it was just derpy. The pistons kept going extended and retracted at the same time. There was block dropping problems, hence these 2-tick repeaters, which I can probably get rid of now. But there you go. So, what is it? Well, it's a number entering mechanism. That's a number displaying mechanism. It's literally just over from the display here. And this is a number entering mechanism. It does the opposite thing. You input a decimal number, and out goes the binary number. So we now have both ends of the system. We can input a decimal number, convert it to binary, give it to the CPU. The CPU can do whatever the hell it wants with it, and then it can print it out in decimal for us, which means we stupid humans don't need to be addled by a poor understanding of binary and hexadecimal, which is great. It makes it easy to read, easy to understand. So this little thing here is quite clever. What it does is it multiplies the last value you put in by 10 and adds your new binary coded decimal value on. And basically it's kind of weird because I've managed to squish this into a single adder. Now what you'd normally do is you'd have the first adder to add your binary coded decimal value to the last value. If you don't understand what I mean, don't worry. But what I realized is that binary coded decimal value has a maximum value of 9, not 16. And we have 3 free bits on the top and 1 free bit on the bottom. So that's 7 and 1, that's 8. We also have the carry in, and the carry in is a value of 1. So we've got a total value of 9. So if we do a little bit of logic here, we can input without a second adder, which speeds it up by a factor of 2 and makes everything much smaller, much more compact, much more elegant. Now, this is again something that's probably been done before many times. I remember seeing a thread of something did similar. I would not be at all surprised if it did exactly the same thing, but I know the guy had an avatar on the Minecraft forum that looked like one of the Muppet characters, but aside from that, I can't for the life of me remember what he called the damn thing or where it was posted. So yeah, it was a long time ago. It was like a year ago. Anyway, so the great thing about this is that you want to enter a number. Let's say I want to enter 125. So 125. And there you go, you've entered the number. Now, I don't have a display on this, but it can be done fairly easy just in VCD without any need for this binary stuff, just over here. So you'll be able to see what you're entering as you entered it. What have we got at the output? Well, we have the 1-bit is high, the 2-bit is low, the 4-bit is high, the 8-bit is high, 16, 32, and 64. Now, 64 plus 32 plus 16 plus 8 plus 4 plus 1 is indeed... Hang on a minute. Yep, it's 125, I think. Yep, if my mental arithmetic is any good, then it's 125. Okay, there you go. There's my super simple binary coded decimal number entry thing. I don't know what to call it. That's just what it is. So, on to my ALU. And you might be thinking, what the hell is an ALU? Now, some of you probably already know, but an ALU is an arithmetic logic unit. It's an abbreviation, obviously, because system engineers and electronic engineers, they love their abbreviations, alright? So, what it generally is it's a clump of circuits that perform arithmetic and logic functions. So you can add numbers together, you can increment numbers, you can subtract numbers, you can invert like a string of bits to change them to something else, or yeah, it's quite simple. It's not particularly advanced or anything, but I like it because I designed it from the ground up, and it's relatively fast. Now it has 2-tick carry extends, 2 of them, so the carry that can propagate through. Let's say we have the worst case scenario for addition. It's got to propagate in here all the way along and right to the end, and the slowest case I could find was 1 second, and that's for a full 20 bits. It would be like 6 ticks for 8 bits, which is not the fastest. I've seen 5 and 4 tick ALUs, but as we all should know by this point, speed comes from intelligent system design and layout, not from having a 4-tick adder as opposed to a 5-tick adder. So there you go. That's my ALU. I designed it myself. It's not particularly fancy. As for control bits, we have invert B down here. We have invert A up here. We have the cut exclusivity, as I call it. Basically, it changes the truth table for the first X norm, allows you to use it as an AND gate or an OR gate. And we have a flood carry line. We have a clear carry line up here. This is the carry in, so that's like add 1 to whatever number's going in. This is the left shift. Now, it doesn't have a right shifter, because you don't need a right shifter, because you can perform a right shift by addition. So you can hide that from the user, pretty much. This is just the left shifter over here, so that performs the equivalent of a division by 2. These 2 lines here, this is the carry out, and that's also joined by the shift underflow, just for one particular design. You can have those separate if you want. And this is the negative line. If the output is negative, that will be a 1, and these are useful for conditions in conditional write back and various things that you want to do in a Minecraft computer. So that brings me rather nicely onto the Minecraft computer. I've built one already. It's a prototype, lots of bits are broken, but I can make it do something interesting for you, and that's why I'm here. So, give me a second. And here it is. This is the full CPU. Well, the prototype, as I say. It's just me testing out the instruction and the architecture, and seeing how hard it is to prototype. I apologise for the cough there. But anyway, first I'm just going to tell you about the instruction, as that usually tells you the most about the machine. Now, this is a very short instruction. It's only 16 bits, but it's still very, very dense. As you can see, like 50% of the torches are in, 50 of them are off, and this is just a standard program. This program performs a software multiplication of 2 numbers from the 2 I/O ports over there, 2 of the input-output ports. So, yeah, I will demonstrate that in a minute. But first, I'll tell you about the instruction. It's kind of ordered funny, but it's still pretty easy to understand. We have the write back location. So this is the register you want to write back. So you put write back to variable 6 or write back to variable 3. Now you can't write back to variable 0 though, because variable 0 doesn't exist. I did this in an attempt to actually speed the machine up, but it turned out not to be necessary, as a small addition to the ALU would mean that you could use your full 8 registers. But for this particular prototype, we've only got 7 general purpose registers. General purpose registers are just temporary storage for whatever number you happen to be calculating. So you've got 7 of those for to use in your programs. Then we have 2 read locations. And these are the 2 read locations you want to use, and these can be used at the same time, obviously, because we've got do read general purpose registers. Some of the instructions will only use one of these, and that's all detailed in a text file that I've written up, which I may or may not release because this thing is buggy, so I may or may not bother releasing this particular one until I've got the final version out. Moving on, This is the operation code. This is just a binary number that describes the operation. Again, this is all listed in the text file, which I won't be releasing, so I'm not sure why I'm telling you about anyway. But that goes into a decoder, controls the various different control bits necessary to make the processor do X or Y operation. And this little 2-bit section is the absolute most important part. This is what makes this architecture so nice. Absolutely any instruction can be conditional. Any of them. Branches, write-backs, any ALU operation, any IO operation, anything that writes back to the general purpose registers can be conditional. And conditional based upon full flags. If it's 0, no condition. If it's any of the other ones, it'll select between some other conditions which are over there on the flag register, which I'll show you later. And last of all, we have the set flags bit. If this is a 1, so you put a torch in there, and the program line is reached, it'll say, right, we need to update the flag register with whatever values are produced by this operation. And that's how you do conditional branching. So if you want to see if a number is negative, you want to branch if one number is bigger than another, let's say. So you subtract the number from one number from the other, and if the result is negative, then one of the numbers is larger and you can branch. If the number is not negative, then it won't branch and you can carry on. So there's your conditional branching or conditional go-to there. Over here we've got the program counter, the decoder. You notice we've only got one decoder for all 4 layers of memory. There are 64 lines of program memory, which is in hindsight a bit excessive unless I do something pretty crazy with it. And we've got a vertical decoder to select the actual level. And that makes things quite a bit more compact and less complicated. Here's the instruction decoder. The 4-bit number goes in, and it just simply decides what control bits are going to go to the rest of the system. There's signs with all the control bits over here. I'm not going to read them out because it'd be very boring, probably wouldn't make much sense. Over here we have the flags. Now, the flags I was talking about, you can write back or branch if the last flagged operation was resulted in a 0, or if it resulted with a carry out, or if the result was negative. So if it was negative, then you can do something like subtraction, and that would be able to tell you whether or not one number is bigger than another. If you XOR numbers together and the answer is 0, then that will tell you that the two numbers are the same. If you use carry out, that's also connected to the shift underflow. Shift overflow happens through the adder, so carry out and shift overflow are actually the same thing. This is just another little simplification. You need to be aware of that when programming this, obviously. That's pretty much it. This is just the little selector for the condition. This one's got a permanent block over it. That's the 0, 0 condition. That's always a 1, so that's always going to write back. This is the RAM. I've not actually written any programs that use the RAM yet. In fact, I'm thinking of omitting it entirely. It's only really useful if you want to construct an array of values, which isn't really feasible or particularly helpful. I guess if you wanted to write a program like Snake, then you could do that, but a program like Snake on a processor like this would be hideously slow anyway, so it's not really an option. Here are the general control bits. This is the program counter control. We can reset the program counter to 0, that moves it to the first line of the code. We can step through, so if I hit this button, it's going to go to the next line of code. If we start the clock, it'll cycle through the lines of code automatically, and if we stop the clock, it will stop cycling through the lines of code automatically. So there you go, and reset PC obviously puts the program counter back to 0 and brings it to the first line of code again, as I already mentioned. Now, as I mentioned earlier, we have a software multiplication program in there. So what we're going to do is we're going to multiply two numbers together. Now this number up the top is 1337, leet, and the bottom number is 101, 101. So we're going to do 101 times 1337, and we should get the output 101111101111000001. Also, did I mention my binary is all backwards? I have the least significant bit over here. That's just how I've always worked, and the most significant bit at that end. And it doesn't really matter which way around you do it, so long as you stay consistent throughout your design, which I have. So, these are the inputs. We've already got them in, as I showed you. We're now going to hit the button, and I'm going to do a quick time lapse of the thing running. So, see you on the flip side. Okay, it has apparently finished the calculation. Let's see if we got the correct answer. Just fly over here, and we do indeed have the correct answer. It has come out correctly. Now, I could go through on screen and I could work out all these binary numbers, but that would be a bit of a pain in the bum, and this is just a prototype, and in the final version I'll hook up displays and various things like the displays and the number entry systems that I had before, so you won't have to deal with binary. But in the meantime, I've just used this. Now, there are more videos coming on this. I will be posting my updates and various things. I'm going to try and stay away from sort of update style videos in the future, so I've actually set up and linked up a Twitter account. I don't like Twitter. It's narcissistic to the extreme, but at least it means I can avoid making update videos. So if something's happening in life and it's preventing me from making a video or whatever's happened, then you'll be able to find information there. There's a link on my channel page if you want to do whatever it is you do on Twitter, follow, I don't know. Just go ahead and do that. So, yeah, that would be about it for this video. I'm sorry it's been a bit hashed together. I'm extremely short on time at the moment. But nonetheless, I hope this was at least mildly interesting to you, and I hope to see you later when the actual 1.5 is up. Sorry, when the actual 1.5 update is released, and I can actually get on with building something serious. So, until next time, see you all later.